Good afternoon. Thank you for introducing this talk. I would like to talk about this statistical machine learning for the DOW data challenge problem. And this project is a collaboration between myself and my former students, Si Guo and Zheyu Li, and also DOW chemical colleagues Liu Chang and Ivan Castillo. Now, the outline is about a short description of the DOW challenge problem, and then on two competing statistical learning methods, partial least squares versus LARS. LARS stands for the least angle regression, which is a recent method for variable selection and biased regression learning. And then I'll show the modeling results and do some analysis and then conclude. The DOW process, the challenge problem is given by this reference a year ago. I think the objective is to build an accurate inferential sensor model to predict the impurity of the product stream from raw data sets. Okay, and this is the product stream. And then we want to predict the impurity. So there are a couple of units here, mainly from the primary column and also the secondary column. There is also a feed column there. These are the predictor variables or the input variables that could be useful to predict the impurity, but it is desirable to select a subset of them so that we can get more robust and accurate predictions. So there are over 40 input variables, and this impurity is the output variable to be predicted. Now, one challenge of this process is that the impurity drifts over time. You can see this is from one low impurity level, then gradually to high impurity level. And there are also other things like the data have missing values and outliers, and also we have to select variables. So we're given two data sets, one for training, the other one for validation, and to show whether the model can predict well or not. So then we have published a paper that's already appearing on the Computers and Chemical Engineering that gives a detailed description of the method adopted in this work. And we basically propose that process operation knowledge needs to be integrated in pretty much every step of the modeling task, from exploratory analysis to outlier detection and pre-processing, and also to model structure selection, and also try to interpret the results and then validate the result. So for those of you who are interested in the detail, you can check that paper. Now, the two competing methods that are popular for this kind of inferential sensors are as follows. One is the partial least squares, and that uses all variables you can find, and that also include a lot of collinear variables. So it's able to handle collinearity by using latent variables, and also PLS will approach ordinary least squares if you use all the latent dimension. Now, the least angle regression, which I'll introduce a little bit later, is related to the lasso, and that will be able to select variables in a greedy way. And then the question we have here is, how does lasso or LARS handle collinearity among predictors? So that's the question. By the way, LARS also has a property that if you get to use the full set of predictors, it will also approach ordinary least squares. So then this is a major question, and also the basis for us to see which methods can do a better job for selecting variables. Now, the LARS method is a stepwise approach. It will first get the y variable and consider no model. So therefore, you just say all the parameter coefficients are 0, and then you start from there. But you try to find the correlation of y to all the variables, and then trying to find the one that's most correlated to y or r for the first step. And then you will do a regression along the most predictable variable. Like if x1 is most predictable, so you'll try to do a model along this direction, and then the residual will go from here to here. Okay, so it's a little hard to see. So the residual will really change, but then when that happens, then the angle between the residual of x1 and x2 will change until they are equal. Okay, so this is the point when the angle between the residual and x1 and x2 are equal. And then if you move further, the angles between x2 will be bigger. So you will start to pick, the angle between x1 will be bigger as you move a little further. So you will stop there and then start to pick the second variable, because that variable has a smaller angle. So that gives the name of least angle regression. So if you have a multiple variables, then you will keep moving along the selected subset of variables until another variable becomes to have a smallest angle. Then you keep that one in the set. So that's the idea. So it's a stepwise method of including variables, and then you have to decide when do you stop. So that's usually done by some index. So now, comparing that method to partial least squares, we can do it like this. This chart on the right shows how partial least squares would do the regression. That will find a subset or a subspace in the x space, that is this direction, and then try to project y orthogonally to that subspace direction, which is the first latent space, or first PLS factor. And then it will find the second PLS direction to be orthogonal to the first one. So there's the second one that's orthogonal to the first one, and then try to get a regression onto the second one orthogonally. So it's kind of picking one direction at a time, similar to the LARS, which will pick one variable at a time. But the difference is for PLS, each direction is a linear combination of all variables. But for LARS, each direction is just one variable that is the winner, okay, that has the largest correlation to the residual at hand. So there are some differences between them, but there are also similarities. Okay, so the question we have here is really this. What if you have a third variable here that's very much collinear to the x1? But then if you move along this direction using LARS, x3 will never be picked by this LARS method. However, x3 is very much similar to x1. So therefore, we can infer that this LARS method tends to pick one of the collinear variables and ignore others. Now, one thing about handling the drifts in the process is that we suggest to use bias learning, or online bias learning. So basically, we assume the model has a bias in it to be estimated, and the way to estimate the bias is using something similar to a Kalman filter. So we tune the Kalman gain in order to predict the output the best. So the filtered estimate of the disturbance or the bias will be added to the model. Okay, and this model would be the PLS model or the LARS model. So now let's check on the DOW data. First, we'll need to determine how many variables in the LARS method. So there is this method called the CP index that allow us to pick one that's kind of giving a small CP number, and then it won't decrease further. So this is looks like 9 variables are good from LARS. For partial least squares, we use cross-validation, and then the cross-validation will say, okay, 6 here latent variables are good to give the minimum cross-validation error. So those are the selected dimensions among the two methods. And then we can see for PLS, they are using all variables with some very small coefficients, some large coefficient, but then LARS will pick one very large one. Okay, and then the first 9 are shown in the blue bars. So that's the two models. Let's see how they perform in terms of predictions. Just for the training part and the test part, we can see LARS will have this amount of training R square, and test-wise is 0.6 something for the test set. And then for PLS, the training is also around 0.8 R square, and the test is around 0.6. So it's not much different, okay? But there are also the testing part is not very good because there is drift. So when we apply the online bias learning, you can see that the training part is 0.9, and then test part is 0.88 for LARS. And then for PLS model with online bias learning, the training part is also again over 0.9, and then the test part is 0.88. So they are very comparable after applying the online bias learning. So really the question here is to understand why these two different models, among the two different models, which one is better? And they seem to have used a very different set of variables, but they gave similar results. So here is one thing we analyzed using this hierarchical clustering. We're trying to see, among this, let's see, the variables that's selected by LARS, this X10 is really the winner, okay? And that's the PC bed 1 delta pressure. And then we'll look at what other variables are highly correlated to X10 by using this clustering analysis based on the correlation. Okay, the distance here is correlation. So it looks like 4 variables are highly correlated to them. So we pick up these 3 and then see where they are for partial least squares. It turns out that these are the 3 variables used by partial least squares, but not used by LARS. And then if you look at all the 4 variables, PLS also pick this X10, okay? And then it looks like LARS had the, really compounded large coefficient on X10, but ignored the other 3 variables, versus PLS sort of used all 4 variables with a kind of averaged coefficients among them. So which one is better? That seems to be dependent on how you are going to use the model. So I will leave it that way and try to conclude here. So basically, LARS tends to select one of the important variables among collinear set, and PLS will use all variables and combine them to latent variables to deal with collinearity. The weights tends to be similar for collinear variables. And then lastly, online bias learning is effective to adapt for process drifts. Thank you very much.